that we have a number of exercises of that type here. I'm talking about completing squares. And I'm looking right now at, well, let's get something nicer, something simpler in terms of reducing the process. Looks like exercise number 50 is here. So the problem here is if you take a denominator and substitute, the derivative of x squared will be 2x, and we don't have 2x. But then when I'm going to look at the formulas for the antiderivatives, I can see the one that deals with a integration of two perfect squares. And those will be a squared and u squared. So if we have a squared added u squared, that's arctangent. Right? So if you integrate it with respect to variable u, a is the constant. Then we have arctangent, and with arctangent, there is a 1 over a that comes out. It's a constant a, and it's coming out in front. And then we have the actual antiderivative, and the antiderivative will be function arctangent of a u over a. Tangent. So the problem is that we don't have nice and clean variable squared and the constant. In other words, when I'm looking at exercise 50, I need to do something with my denominator. So I need to rewrite it with only x, and then whatever with x could be squared. So the process of completing the squares is pretty standard, and it wants to look at first two terms and take a half of what's with x. So half, so in other words, 2x, x squared. So maybe I can just write it down again and put that plus 9 somewhere away. So that way is better. So half of 4x will be 2x. So what we do is we add 2 and then square it, and then we subtract 2. So add, subtract, the same thing, doesn't matter for the whole thing, but the point is that we now can put this as a perfect square of x minus 2. So if you decide to verify it, you multiply x minus 2 by x minus 2, it will give you first term squared, and then 2 squared with a plus sign, and then 2 times x and negative 2 will give you minus 4x. So that's first part, and whatever remains will be minus 4 and 9, which is plus 5, that's the second part. So that way, I can rewrite my antiderivative of 1 over this x minus 2 and the parentheses squared and plus, now it's 5, so I can write it as a square root of 5 squared. Do that little trick, and dx is on the top. 1 dx and just dx. So the point is I can match it with the formula. So then what? Well, then technically it will be a substitution x minus 2, but I don't really need to do it. It's just going to be dx, that's derivative of it. So I could utilize 1 over a. So my a here will be, I think it's worth to notice that a here is square root 2, the constant. And instead of u, I put that other p. That's going to be my u. So 1 over a. Why is that 1 over a? Well, that's the formula. 1 over a. So it'd be 1 over square root of 2. And then we have our arctangent function. Arctangent. And then again, denominator will be a square root of 2 because it's over a. And arctangent is taken off whatever is in the parentheses, x minus 2 and plus constant. So the process of completing of squares will be utilized here, everywhere where you have, well, not here, yeah, here as well, where you have x squared and there. So there are lots of little exercises. So if you feel like it, you can try to complete squares on one of those. But again, that's not the point of today's story, because today's story utilizes the examples where you cannot do substitution. For example, if you will take a look at the process of integration by parts, it has a special name. If you try to recall the process of taking the derivative of product, remember derivative of u times v is u prime v plus v prime u. So that's the formula that, again, was discussed in Calculus 1 class. And then what you do is you try to clear denominators. So you multiply by dx both sides of this equation, so that dx's will disappear here and basically everywhere. So you end up with a uv, which is u times dv. So if you want to now integrate it, you will end up with uv, which is u times dv. Right. U times dv plus v times du. And that way, when you're gonna integrate it, you're gonna end up with that piece dv, or dv over dx times dx. So you could treat it as if it was v prime dx integrated, and the other piece integrated will give you the other one. And the idea of the formula is, just write it down. So it's coming from the derivative of product, that integral of u times dv, or actually, it doesn't really matter. You can pull out u dv or v du, any of those. So u dv, for example, is uv minus integral. So you just bring v du on the other side of v du. So why this is useful and why this makes sense? Well, in a case when you have integrals that you cannot take by using the substitution. So let me try to show you an example. So I can just do one problem here. Let's say, what about if you, what is this? This thing appeared. So we have, let's say, exercise 1, or let me do 1. If you try to substitute, you wouldn't be able to do anything here, because the problem is with having a product of x times dx. But what people do is they take derivative of x and it becomes 1, and that's what enables you to integrate. So they call it as a U, and this other whole thing is dv. So they use formula. So what they say that x is equal to u, and whatever remains, they call as dv. And one portion they differentiate, and the other portion they integrate. So if you take derivative of the first substitution and antiderivative of the second, so what would you get then? Well, derivative of x is 1, so it'd be just 1 dx, and whatever u was, so you put as du. So in other words, if you write du over dx is equal to 1, and then bring dx to the other side. And you can take antiderivative of e to the power of 2x. Antiderivative of e to the power is the same thing, but 2 will go down to denominator, because when you decide to go back by taking the actual derivative, 2x will spit out 2, and it has to be canceled by the 2 on denominator, so that should be getting just e to the power of 2x. And antiderivative will be. So then I will follow to the formula. So I need to set up a product uv minus vdu. Miss Alex, why do you do that? And the answer is because now I'm going to get nice antiderivative, because my problem was here, product. So look at that. What is u times v? What was for u? That was x. What is v? That's here, e to the power whatever. Let's see, but you still have a product. Yes, but no longer anti-differentiated. It's already the answer. It's already nice. There is no integral sign. But there is still be integral of vdu, but look at what we're integrating. Now it is nice. Now it is not a product. Look at this. It's just e to the power, and it's multiplied by du, which is dx. So you no longer encounter a product inside the antiderivative. So it's an analog of derivative of product, u times v. So it's antiderivative of product. And this idea is that we don't really need to have a product integrated any longer. So we can find that antiderivative of e to the power of 2x. We just did it, right? It was same thing, but over 2. And there is still that other 2 on the bottom in denominators will be times 2. And whatever we have from the first piece, I just copy, trying to get it. So I just copy this x, whatever it is. So the point is we took antiderivative. We no longer have integral sign plus the constant. So that's the idea. And that's exactly what they're talking about when they utilize the usage of this formula. And this whole section is about utilizing this formula. And where's the formula? It's right here. u dv is uv minus vdu. So that's theorem 8.1. That's the one that was justified in here. It is useful when you integrate various functions that you could not integrate otherwise. And here's the looking at the example similar to one I just did. It was just e to the power of x, not 2x. So that's another interesting procedure. So I can show you the groups of functions where you really need it. For example, ln. So whenever you have your natural logarithm, you have to use parts, the finding of antiderivative by using integration by parts process. So let me clean this mess a little bit. And try to do one exercise with logarithms. Again, I don't want to copy exactly the same thing here. I think it's interesting to do it yourself. So I can just go back to the exercise set and select problem with ln. So that's another group of exercises where the integration by parts is the only way to do the problem. So for example, like exercise like 19, wherever you see ln, usually you have to use parts. Sometimes you don't. Like in 19, actually, you don't need to use parts. You can do the substitution, but let me do one where I must use parts. And this will be exercise like 24 because it's x squared. So let me do 24. And then I'll do 19 and show you why I don't need to use parts. Well, technically, you could do it also by parts, but they say simplest method. So parts is not considered the simplest method. You usually utilize it when you don't have the substitution that you can use. But technically, you could take problems and do it various way you like. So here's dx over x squared. So I'm going to write it in such a way that I prepared my ln to disappear. So again, the point is utilize the formula in the upper left corner. So that way we can replace with a u our ln. And the reason is we are replacing it with a u because we can take derivative. Remember, the derivative of ln derivative is 1 over x. And that's main idea. Get rid of that natural logarithm. So that's what I'm going to successfully do now. So we call ln 2x as a u. Do you remember the formula? Again, it's been a while, I know, but in a Calc 1, that's the very popular formula we use. And then the rest is dv. So I can prepare it for finding antiderivative by writing x to the power of negative 2 dx. It's dv. Because we're going to use favorite power rule for finding antiderivatives. So the left side, the first I differentiate, and the second I integrate. And it's always like that. Always means always. So standard process. So take the derivative of ln, and that will be 1 over 2x, right, using the formula here. And then I multiply it by derivative of, by the chain rule, what's in the parentheses, and that be by 2. So that's my derivative, and that's dx must be attached and equals to du. So we prepared already du. Please notice that the 2's will nicely cancel, and that's great to know. I love to cancel. So it's just going to be 1 over x. Okay, so for the second one, I take antiderivative, so I need to add 1 with negative 2, and this will be negative 1. And then I put this minus 1 then in denominator. That's standard. Nice, and v is coming out. So what is v? Maybe I'll write it again. V is going to be negative 1 over x. That's better, right? That's better looking thing. So that's the one that I will use now when I, excuse me, again, set up my formula, uv minus integral of v du. So that's the whole point. Once you do it a couple of times, I'm sure you start to feel better because, yeah, when I saw it first time in my life, I was just very confused, wondering what is going on here. And well, later on, I understood and appreciated because it's helping to take antiderivative. So I have to multiply u by v, and v is that negative whatever, 1 over x. Okay. So the first piece is already taken care of, no more integral, but the second piece I have to integrate v du. So I have to integrate v. Maybe I'll write it with a power of -1, right? You have, or actually, no, I better just keep it as 1 over x, because if I try to integrate 1 over x, there'll be nice thing happens. Integrate it and you get ln, right? See, Alex, you're gonna return back to ln? Yes, but that will be already the answer. So it's not a problem. It's good. It's a good one, ln. It's not inside the antiderivative. So let me prepare to do that. So minus 1 over x v, right? Let's say 2 minuses will give us plus. Yeah, we'll do it later. And then du is going to be 1 over x dx. Oh, please notice that we're going to have to integrate 1 over x squared once again. And we just did. And usually, pretty much in all the examples, but not 100%, but pretty much, you will repeat the integration that you just did here once again, once you get rid of that product, so you just have one piece. So you end up with integrating of x squared and denominator, so power of -2 over du. So dx. Okay, so let's write down what's for the answer. ln of 2x over x is one piece, just copy. And the other piece is going to be we just did it, right? X squared, so it's again x squared. So we go with the -1 over x and constant. So don't forget about plus the constant, that's important. And whatever you have with the lens, you will pretty much always utilize integration by parts, but for some exercises like number 19, it is not necessary because you could use substitution, turns out. Because ln x, as usual, is the part that bothers us, but if you replace it with a new variable u, so if I try to do exercise 19, replace ln x with u, then its derivative will be exactly what I have on the bottom, will be 1 over x. Okay? It's dx is t. So that's the only case where you can use substitution, when its derivative is going to be exactly what you have on the bottom. Then it works. Because if on the bottom was x squared or something, x square root x, whatever, you wouldn't be able to do the substitution. Then you would need to do parts. But for this particular example, you end up with nice integrable expression. So ln is squared here, so I put u squared. That's my top. And 1 over x dx is exactly whatever is remaining, so that'd be times du. So there is nothing on the bottom, so you can see 1, or just don't put anything, and that way you will get u cubed over 3 and constant. So that's a favorite procedure. And now you need to write back your original variable x, right? So it's ln of x cubed. So that's why we always try to see if, when you differentiate your ln, everything that remains besides the constants will actually be whatever we have here, but in exercises like problem 24, the derivative of ln was 1 over x, so x squared, so it did not allow me to do that. Well, interesting story happens, well, analogous with sines and cosines, so derivative of x will be 1, so the product, see, the problem is products. So we take derivative of x, it disappears, and cosine, we can take derivative or antiderivative. It's not hard, and we'll get something here. Now, exercise like 30, you'll need to do parts 2 times because you need to kill nx squared, so it'll be x, and then x, so it'll give you the first power. So maybe I can do that now. So sometimes you have to use parts twice or 3 times or as many times as the power of x is. And it is kind of annoying just doing the same thing again and again. But let's do one exercise here because I don't think they will ask you to do x to the power of 5 times this function, but x squared is usually where they get to. So let me do exercise number 30 or 29. You'll have to do it 3 times. So I'll do 30, 2 times. If you feel like it, maybe you can try 29 just for fun. But anyways, x squared is multiplied by cosine. So once again, I'm going to take and again, you might ask me if you want me to do some exercises of your choice. I'm trying to be consistent, so little by little moving along with these. But if somebody wants urgently to do a problem, please let me know. We'll do it. So anyways, x squared is my u, and cosine is dv, whatever it means. I say, Alex, what if I tried to put for the u letter cosine function? Well, notice that you'll need to then integrate x cube, and that will x squared, and that will give you x cube. So it's not gonna help, and that's what you probably want to try on your own, just to convince yourself that we don't have really a choice for using parts. So if I take derivative, it will be 2x dx. So sometimes you try to substitute incorrectly or to do parts incorrectly, and then you will see that it's not helping but making things worse. So you'll return back and tackle the problem again by calling, instead of u, that part as a u, and then the rest x squared dx dv. So that's what people sometimes end up with. So anyways, sine, right? As antiderivative, and it's v. When you say, Alex, but plus the constant, well, turns out that's a function of x, so it may be observed by function v. So now I need to again produce my new favorite structure, uv minus integral of v du. So let's see what it's going to be, u times v. So u is x squared times sine x, right? Sine x. And then we subtract from it integral of v du. So I have to integrate again v. I put sine, and then times 2x dx. So what happened now? I still have a problem. I still have a product of x. But power of x used to be 2, and now it is just 1. So I'll have to do parts once again, which is, I guess, a little bit annoying, but it'd be the last thing to do. So I will call again 2x as a u. Alex, why don't you call sine? Well, because if I integrate 2x, it'll give me x squared over 2, so I'll return back to x squared structure, so we don't need to do that. That's why I want to make sure that I take derivative of 2x so it becomes just a 2. And that's why I call it as a u. That's my u. And whatever remains, sine x dx, that's dv. Okay. So once again, we integrate and differentiate. So you take derivative of the first, antiderivative of the second. Okay, so derivative of the first will be 2, only 2, because derivative of x is 1, so it'd be 2 dx. Just trying to write 2 here. And that's third time to write 2. And that's my du. And then negative cosine, right? Derivative of cosine is sine with a minus. And minus will then be absorbed. So I have to put extra minus, and that's my. So I'll write it last time, uv minus vdu. But remember what we were doing here? You say, Alex, I already forgot. Well, this piece is already in my answer. So that x squared sine x is already here. I just copy. And then I have to subtract from it. And then I have to subtract from it. And now I'm taking that antiderivative. So whatever we're doing here, that uv minus v du, we have to subtract. So I just copy the previous result and uv. Now it's going to be product of these two guys. U is 2x and v is negative, so I put minus in front, so it'll be 2x times the sine of x. So whatever comes out, again, we don't really care for. We just put uv, and then minus, so it'll be minus, and that's integral of v du. And now look at that, integral of v. That's negative cosine. And then we have times du, which is no x times 2. And that's great. This is my last integration that I will perform. I can integrate cosine, right? Again, get sine. So let me finish up. So 2 times I did the process. So I'm sure after you really want to probably get a piece of paper and do it yourself. Again, the same exercise, and then you will be proficient at the process of integration by parts. So I'm just copying whatever we have so far, first 2 terms here. I just copied them, 2 minuses is plus. Now 2 minuses is going to be plus, and then sine, right, antiderivative of cosine. But times 2, so that's 2 that comes out in front, and then plus the constant. We're done. Well, with integration by parts, sometimes, so you can see you need to do 2 times antiderivatives process, and that's sometimes a standard. That's what I want to show you now. And well, I would say that'd be a little bit too much for me to assign to you for you to do, but you might encounter it if you be taking differential equations class. For sure, you will be encountering it. It's so-called cycle-like process. So let me find integral. Example 5, secant cube. So what they do is they trying to lower this to integral. So they nicely wrote everything. So they want to split secant cube to secant. Why do I write secant? to the first power and then times secant squared. So it's preparation. So that way you have u, and that's dv, right? And they write, if you take dv, then if you integrate secant squared, that's tangent. So that's my v. So I can prepare, right? uv minus v du. So uv. So when they take the antiderivative of secant squared, antiderivative of v is tangent. And then when they take derivative of secant, it's secant tangent. I say, really? Well, 1 over cosine. Cosine is in denominator, so denominator will be squared. Let me write it here. Maybe here. Secant, so that's 1 over cosine. It's worse to write it once. So denominator is squared. So cosine squared. And derivative of numerator is 1 times denominator, which is cosine, minus, I say it's probably easier if you just, yeah. Well, anyways, it doesn't really matter. So derivative of cosine is negative sine, so it'd be positive sine of x times denominator cosine. Okay. So am I getting closer to what I need? Well, look at, or I should have probably just treated it cosinus. Yeah, it'd be better visible. Because now I need to do some trigonometry on this factor, and then it's be a little bit too much. Maybe a bit better do it like that. So just use chain rule. Instead of, here's a quotient rule. So f over g, so that's a little bit too much. Chain rule is always better, so I was not thinking clearly. So the chain rule does what? Negative 1 puts in front of cosine of x, right? So derivative. The power is in front, and the power will be squared. And then I have to multiply it by a derivative of cosine. So I took care of negative 1, derivative of cosine is negative sine. Yeah, that's better. Because negative and negative will give me positive cosine of positive sine of x. And then cosine I will write as, so it's cosine squared in denominator. So I can write it as cosine times cosine. You got to dead end. Sometimes you started doing one way and then you need to start over again. So sine over cosine is going to be tangent, and 1 over cosine is secant. Right? Sine over cosine is tangent times 1 over cosine is secant. So secant tangent. So you can always verify it, but some people just memorize the derivative of secant is secant tangent, because antiderivative of secant tangent is secant. I guess, again, it's a good idea to sit down and to write it. But anyways, what we produced here is u and v and du, and we also have dv. So let's put everything we need down here. So we are going to go for the uv. So our u and v will be tangent. So that's the part that we're good with. I'm not gonna write x, I just put tangent. And so that's u, and v is secant or secant tangent. secant minus, so that's u times v, u and v, minus integral of v du. So minus integral of tangent times du, which is secant tangent. I think I need some clear some messes. Messing with me. So that's what they actually do in here in the next row as well. So it looks like what they did is clean this mess. They put tangent times tangent, so it's tangent squared. So it's always kind of fun to trace what they wrote, right? And make sure that you are on the same page. So that tangent and tangent give you tangent squared and then secant. So that's what you're subtracting, and that's UV tangent secant or secant tangent. And then you're gonna need to do a little bit of trick. So instead of tangent, you write secant squared minus 1. So that's identity. So that's all they did on the next step. And then when they distribute, they get that secant cube and integral of secant. So please notice that's the key part. They have integral of secant cube, and here they have another integral of secant cube. So they bring it to the other side. So they have two integral secant cube, and whatever is left, so that's already something that you don't need to integrate, right? And that's the part you need to integrate. And antiderivative of secant is ln secant plus tangent. That's table integral. And you ended up with, now you need to divide by 2, so you take 1/2 of this, and that's why 1/2 appears on the left side, and you end up with what integral of secant cube is. So you were not able to take the antiderivative, but you did the trick, algebraic trick. You presented that secant cube with something plus the integral of secant cube by itself. How about that? And that the integral of secant cube we brought to the other side and solve equation with respect to it and was able to find it. Which is a trick, which is something I wanted to show you, but again, I guess that'd be pretty much all it is. I'll just do one more exercise. I think that should be good enough. So what I saw, arc cosine, I think that will be good to look at. So maybe I'll clean the mess. It's actually pretty much cleaned. So just try to write it again. So exercise number 34. Just like with the logarithm, the issue is with taking antiderivative of arc functions, arc cosine. But I can take its derivative. What's the derivative of arc cosine? Well, it'd be the same thing as for arc sine, but with a negative in front. So derivative of arc sine, or arc sine is 1 minus x squared, but with minus 1. So they always differ by the minus sign. Again, I need to know that. That's something that people need to, I guess, have tables, and that's the one that I have to utilize in here, because since I have a function that I cannot integrate, well, I'll do the parts and I will differentiate. So that's why parts are so important. So I take arc cosine, takes a while to write, as a u. And what's for dv? Well, Whatever is left, whatever is left. So dx will be my dv. Can this be done? Yes, of course, because I want to take derivative. So now I'll be good. Now I'll get rid of that arc cosine that bothered me. And of course, I can integrate. So for the other, I don't really care. So if I take derivative, that'd be my -4. See, the negative sign comes out over the square root of 1 minus x squared. And when I keep, right, to the derivative of arc cosine, that's dx, my du, and derivative of 1. So that was dx. So derivative of 1 dx will be this x, because derivative of x is 1. It's 1 dx. Yes. And that will save me now, because when I set up my new favorite structure, uv minus v du integrated, the second piece will be good. Look at that. So u times v, that's the one I don't care for. So u and v are here. So that's already coming out as the answer. So I can put u, which is for arc cosines. X times v, which is times x. But now look at what I get, and that's going to make you happy. V, which is x times du for arc cosine du. So that'd be -4, there it is, dx. It's no good, but it will be very good for substitution. Because this stuff I don't care for, I just care to take the antiderivative now. So let me use the color. So with antiderivative, look at that. 1 minus x squared, which is inside of square root, I can call as new variable. So uv, I don't want to use, maybe z. So when I take its derivative, it will become negative. Right? Derivative of 1 is 0, so it's -2 times x, with dx is my dz. And that x will be absorbed. And that's what's going to make me very happy, because now this x and dx are going to be absorbed. I say, well, there's 2x, but you have 4. Well, it doesn't matter. 4, you can put a -2 times 2. So -2 is also going to be absorbed. So instead of all this stuff that I circled, I put blue color. So I need to copy that arc cosine again. Arc cosine. That's probably why sometimes they like to write cosine inverse, because that's annoying to write very long. Arc cosine of x times x. It's entire factor times x. I probably should have brought x in front, and then minus. And what we have is a new integrand that we'll be able to get rid of. X minus 2 and dx become dz, right? That's my numerator. And then my denominator end up with the square root of c. And that's the one I can take, right? Because, again, if I try to integrate, let me write it again so you'll be clear. So z square root would be power of 1/2 And since in denominator is negative sign, dz for all text, dz. And then you use the favorite power rule. So you add 1. So 1 and negative 1/2 is positive 1/2. So you have to put same in denominator. And then we plus the constant, of course. And then we replace back z with, so 1/2 I need to divide. So I multiply by 2/1. And the square root of z will give me square root of, I go back to my original variable, 1 minus x squared. Okay. So that's my square root of z. And then we'll write the answer finally, and we'll be done. So finally, the answer is coming out. It'd be that 4x, I put in front. See, with arc cosine, or sometimes they put the power of -1. So that's arc cosine. You can put with arc or with cosine inverse. And say, why is that? Well, I don't know. They just to make it short. And then we subtract whatever we produced in here, and that was 2 square roots of 1 minus x squared. And we're done. Put plus the constant. So I think it's plenty for today. I just need to add one more thing. I will be emailing you the practice for the midterm. So the midterm cutoff will be here at this stage. And the homework, remember, I was asking you to send me like one problem, 2 if you did more. Each one would be enough, because looks like they were pretty lengthy, right? So one problem from each lecture. So we had a bunch of lectures, and from each lecture you can select anything you like and copy it and email it. So I will, of course, email you a recording of this lecture as well. So did you know I was emailing you a recording? So for every lecture, I am recording it right now. So I will stop recording soon and email you this lecture recording as well. And you could just check those recordings, and you could just copy the same problems I did. If you don't want to copy, you wouldn't do something else for fun. So you can try 33, very similar to 34 if you want to, but you don't have to. I'm going to tell you the secret. I will ask you to do arc cosine on the midterm. In fact, I will be emailing you the practice exercise for the midterm, and we will discuss it together on Thursday. And you will know this way for sure exactly what will be on the midterm. You don't have to look at all these actions we went through. So just check your email a little later today, and you will see what will be on the midterm. And I will actually work it out for you on Thursday. So you will also know how I did that exercise. But of course, I will change numbers. So the reason I'm sending it to you, because everybody's going to get different. I say, what's different? Well, it'd be somebody's going to get 2 arc cosines, and somebody else will get 3 arc cosines, somebody else will get 5 arc cosines. So the answer is not going to be identical, but the problem will be the same. To me, it doesn't matter what the constant is. It's just different constants to make sure that the answers are not identical for the whole class, because it's kind of a joke, right? If you give the same exam to everybody to take it home, plus I don't limit you on time. You can take it within 1 day or 2 days or even a week. You can take so much time as you want, and if you decide that you want to redo it, fine with me. You can redo it, but that's the idea. But we'll discuss all that next time. So check your emails a little later. You will see the practice exercises in your email. And I think that'd be a great for practice and to make sure that you feel comfortable. So you feel that you are safe, you're going to do great. I want you to ace this class. grade A, right? So please keep that in mind. So anyways, let me stop to record, see if you have any questions, please ask. And if no questions at